You hear when there is sound.
You see when there's light. There is an array of sound and light around us.
We can tell the difference between the sound made by musical instruments and the noise generated by machines.
And we can also distinguish the 7 colors of the rainbow. However, there are still some sounds and lights that we can't hear or see.
For example, the sound of very low frequency through which blue whales and giraffes communicate with their kinds and the ultrasounds that dolphins, dogs and bats can hear are beyond the threshold of hearing for humans.
At the same time, we can't see microwaves, infrared or ultraviolet light with the naked eyes.
The physical properties of sound and light are different. Sound requires a medium for transmission, while light can propagate even in a vacuum.
Both sound and light, however, obey the laws of wave and that they both enable us to connect with everything in the world as we perceive them. Let's investigate the laws of sound and light now. What makes it possible for us to hear?
If I put a vibrating tuning fork on the tabletop, the bean sitting on the tabletop will jump up and down.
Why is this?
Let's replay in slow motion so we can see it more clearly. Let's pay attention to one more thing. When we tap the tuning fork, the 2 arms of the fork vibrate vigorously. The tuning fork can generate sound because its vibration causes the air particles around it to vibrate. When these vibrations reach our ears, they cause our eardrums to vibrate, which creates sound as we know it. Therefore, we say that the tuning fork generates sound. A violin generates sound because the vibrations of the strings cause the air particles around it to vibrate.
How can air particles vibrate?
Here is a subwoofer, which is commonly known as a loudspeaker. It generates sound when the diaphragm vibrates inwards and outwards.
When the speaker's diaphragm vibrates inwards, the density of the air particles around it reduces and an air rarefaction is formed. When the diaphragm vibrates outwards, the density of the air particles around it becomes higher and an air compression is formed. Each time the diaphragm vibrates inwards and outwards, it results in compression and rarefaction in the surrounding air, and the vibrations are transmitted in this manner. The air itself doesn't move, it just vibrates to and fro. This alternation of the compression and rarefaction generates waves. That is why sound is also called the compression and rarefaction wave or sound wave.
Even a slinky spring can generate sound waves. Place a slinky spring on a table and stretch it so that it is in a state of tension. Fix the position of one end of the spring and hold the other end in your hand. Now pull the spring back and forth.
Compression and rarefaction will occur alternately. You will notice that the compression and the rarefaction will propagate forward. This is called the compression and rarefaction wave. Although we can't see how the air particles move, their movement as sound propagate in the air is very similar to the movement of the spring.
Now let's label a fixed point on the spring and watch its movement. When the spring vibrates, the fixed point won't move to the left or to the right. Instead, it oscillates repeatedly to and fro at the same point. When the sound is propagated in the air itself doesn't move. It merely vibrates back and forth at the same point, and the wave can propagate outward.
Can there be sound in the absence of air?
The true nature of sound lies in the vibrations of substances. It propagates as waves. In the air, sound is propagated as refraction and compression waves. Accordingly, it is possible for sound to propagate in liquids and even in solids.
Think about it. How do those things communicate with their companions in the water? The clue is already there.
That's right, they make sounds in water.
In fact, we've all had similar experience. When we are underwater, we can hear the sounds generated by the vibration of various fishes, objects, engines of vessels, or even musical instruments.
This little design can help us to hear sound. It also proves that sound can be transmitted through liquid. As for the transmission of sound in solids, we actually often encounter this in our everyday life. Well, we often hear this, to be exact. Have you ever heard of the saying, walls have ears?
If you speak against a wall or knock it, the vibrations of the sound will be transmitted into the wall and then to the other side of it, setting in the air on the other side in vibration and generating sound.
The wave that propagates in walls is also a sound wave. It may be hard to imagine, but compression and refraction do take place inside a solid, although not as vigorously as in the air. The difference between transmitting sound through the air and through a solid is that sound propagates in a solid not only as compression and refraction waves, but also as other forms of sound waves.
Many people have the misconception that sound is something in the air. In fact, sound is the result of vibration of substance. It can be classified into different types according to different modes of vibration. Compression and rarefaction waves can propagate through gases, liquids, and solids. And the speed of propagation is not the same in different media. Guess whether sound is propagated faster in the air, or in the water, or in metal.
Once again, sound is the vibration of substances when it is transmitted through a medium.
I'm sure we've all experienced this when we watched fireworks. We see the fireworks set off brilliantly high in the sky before we hear the loud sounds of bang bang. When fireworks are set off, what actually happens is that the sounds are generated first before the beautiful colors are released into the sky by the exploding gunpowder. In other words, the sounds of fireworks are generated before the brilliant display of lights.
But why is it that we see the light before we hear the sounds?
This is due to the speeds of the waves. Sound travels through air at a speed of 340 meters per second, whereas light travels through air at a speed of 300,000 kilometers per second. Although the light is generated later than the sound, light travels much faster than sound. By the time we hear the blasting sound of the fireworks, the distance traveled by the light is long enough for it to travel around the Earth several times.
Why is there such a big difference in the speeds at which light and sound travel?
It is because sound is the result of vibration in substance, while light the oscillation of electromagnetic fields. They are vibrations of two different natures.
Sound is caused by mechanical vibrations, and it requires a medium for propagation. The particles vibrate in the same direction as that of waves. We call these longitudinal waves. But light is an electromagnetic wave, and that the oscillations of the electric field and magnetic field are perpendicular to each other. Also, it does not need a medium for propagation. Moreover, the direction of propagation of the wave is perpendicular to that of the electromagnetic field. We call these transverse waves.
As light does not require a medium for transmission, it travels faster in vacuum, nearly the same speed in air, but reduced to 230 km per second in water and further to 200 km per second in glass.
The speed of sound is the exact opposite. Sound requires a medium for transmission. It travels about 4 times faster through water than through air, and about 15 times faster through metal. Basically, the denser the medium, the faster sound travels. However, no matter how fast sound travels, its highest speed would only be 100,000th that of light. The speeds of light and sound are simply incomparable.
Although the natures of sound and light are different, they exhibit very similar behavior. Is it possible that they do share some things in common?
Can you tell apart high, medium, and low-pitched sounds?
What factors determine the high or low pitch of sound?
Treble, alto, and bass sounds are generated from different drivers in a loudspeaker system respectively, so the answer might be there.
When generating sound, the diaphragm of the tweeter vibrates so frequently that it's almost impossible to see its movement. In contrast, the vibrations of a roofer's diaphragm are relatively slower, and it's not difficult to see the diaphragm oscillating back and forth.
The frequency of vibration determines the pitch of the sound. The more frequently the air particles vibrate, the higher the pitch. Likewise, the less frequent the vibration, the lower the pitch. Frequency is defined as the number of vibrations per second, and its unit is Hertz. Remember, the air particles are only vibrating back and forth, and they do not leave their original positions at all.
Well, then what determines the loudness of sound?
Here is a large drum. The frequency of vibration will be the same no matter how hard or how lightly I beat it. But if I beat it harder, the sound it makes is louder. Whereas if I beat it lightly, the sound produced is softer.
So what determines the loudness of sound?
If we look at the vibrations of the drum when it is beaten powerfully in slow motion, we will see that the amplitude of the vibration of the drum's diaphragm is greater than that when the drum is beaten more lightly. That's right, it's the amplitude. When the diaphragm of the drum vibrates more vigorously, the air particles are made to vibrate back and forth to a greater degree. In other words, the amplitude is greater.
Why does it make the sound louder?
It is because the intensity of the sound is related to the amplitude of the vibration of the air particles. The greater the amplitude of the vibration, the louder the sound becomes. Sound propagates in the air in the form of refraction and compression waves. When we beat the drum more powerfully, the vibrating drum diaphragm will set the surrounding air particles in a very dense compression and very sparse refraction. The density of air particles is also related to air pressure. The higher the air density, the greater the air pressure. The lower the air density, the lower the air pressure. The big difference between the air pressure of refraction and compression creates such an effect on the eardrum that a loud sound is perceived. When the amplitude of the vibration is smaller, there is only a slight difference between the not-so-dense compression and the not-so-sparse refraction. As a result, the difference in air pressure is smaller, and so a softer sound is perceived. This is what the loudness of sound truly means. The greater the amplitude of the vibration, the greater the difference between the density of the air particles of compression and rarefaction. The louder sound becomes. Conversely, the smaller the amplitude of the vibration, the smaller the difference between the density of the air particles of compression and rarefaction, and the quieter the sound becomes. Although light has a different nature to sound, they have properties in common. While the color of light is determined by its frequency, and the intensity of light is determined by the amplitude of the vibration.